All right, so I just want to do a couple more big O examples for you. To remind you, we say f is big O of g if there exist constants c and k positive such that for all n greater than or equal to k, we have that the absolute value of f of n is less than or equal to c times the absolute value of g of n. And we're going to be typically ignoring those absolute values. Let's do an example. Let's show that, let's say 3n squared plus 7 is big O of n squared. Okay? So if you remember the previous example, the way we did this was we just sort of picked a constant that worked. In this case, we picked the leading coefficient. And that worked because, or one of the reasons that worked is because we had something times n squared, which we were showing was n cubed, and this is strictly less than this. However, here, we've got the degrees match. And one of the things you can do, I mean, if you watch some other videos or look some things up, you'll see that there are lots of little tricks. But one of the sort of little tricks that I like to do is just to add up all the coefficients for my constant. So, solution, we're going to pick c equals 3 plus 7. So I'm just adding up all those coefficients, which in this case is 10. Because there's no like lower limit for the constant. Once you find a constant, any bigger constant will work. You just need it to be big enough. If you want to, you could pick 1,000,000 every time. It just might make some of the later calculations a little bit more uncomfortable. But for this case, we're going to pick 3 plus 7 because we got 3 and 7 there. And now we need to find a suitable k. And by a suitable k, I mean a k that we can have for all n greater than k, we got this thing. Greater than or equal to k, we get that thing. So let's just write this thing down, what we want. What we want is the absolute value of f of n less than or equal to c times the absolute value of g of n, which in this case, with this c, so this is going to happen if and only if we have what? Well, I'm going to assume that k is positive, so we have that all of our n values are going to be at least positive, meaning, if n's positive, this is positive, and this is positive. So we can drop the absolute values, and I've got 3n squared plus 7 less than or equal to 10 times n squared. All right, now I want to get n on its own, so I can say n is greater than something to make this thing true. And again, this is just a technique. You don't have to do it this way. Well, this is going to happen if and only if what? Well, let's subtract let's subtract 3n squared from both sides. So minus 3n squared minus 3n squared. And I'm going to get 7 is less than or equal to 7n squared, which happens if and only if. Divide both sides by 7. This happens if and only if 1 is less than or equal to n squared. And if 1 is less than or equal to n squared, I have that these things are just gonna keep holding for any bigger values. Then I can safely pick k equal to 1, and that's because this is essentially like I guess I kind of skipped a step here. This is essentially saying I can take the square root of both sides, and I'll get n is bigger than or equal to 1. And because that, I'm going to pick k equal to 1. So this is like my k appearing here. All right, and since I've picked my c and I've picked my k, and this, as I've gone through these calculations one way, I could also go back the other way. This satisfies my big O criterion. And so for the sake of this class, I would let you stop here. I'm just going to go back and do a little bit of extra work to show you why this verifies this, or why this c and k are suitable witnesses. Remember, these are called witnesses. I think I mentioned that in the previous video. Yeah, called witnesses. All right, so what am I saying here? Okay, we notice for all n greater than or equal to 1, I have that 3n squared plus 7 is less than or equal to 10n squared. That's what I've just shown. So this is plugging in my c and k. And we can see this happens because again, just following through the same calculation, if we subtract 3n squared from both sides, this is saying 7 is less than 7n squared, which is basically just saying n is bigger than or equal to 1. Now again, some of you might be like, well, but wait a minute, don't we need n is bigger than plus or minus 1? Well, that's fine. You can look for more difficult things to happen, but if I'm telling you n is positive, then I'm just going to ignore the negative numbers. Moreover, the situation can get more subtle than that, but all I need is the biggest one that works. And once I find a big one that works, anything bigger will also work. So this is good for us here. All right, let's do another one. Let's show that n squared is not big O of n. All right, to see this, we're going to prove this by way of contradiction. By way of contradiction, suppose n squared is big O of n. Well, that would imply that there exist constants c and k positive such that for all n greater than or equal to k, we have n squared is less than or equal to c times n. I guess I should put in these absolute values. Now, because these are positive, this tells me that I can get rid of the absolute values. So this is just saying n squared is less than or equal to c times n. Let's divide both sides by n. And I get that n is less than or equal to c. But this has to hold for all sufficiently large n. And it's not true that all sufficiently large n are smaller than any constant that I pick. So I'm sort of, no matter how big of a number c that I pick, a billion, a trillion, a quadrillion, whatever I pick, there's always going to be an n bigger than that. So we've got a contradiction here. Okay, and that was fast and slick. So I want to go kind of back over it slowly. A lot of people see this and they're like, wait, what happened? Okay, so recall that we're trying to prove this by way of contradiction, right? I'm trying to show that n squared is not big O of n. So I do that by supposing that it is. So suppose n squared is big O of n, then that means that these constants exist, c and k, and I don't necessarily know what they are, but that just means that there exist constants such that for all n bigger than the first constant, math implies n is smaller than the second constant. So there's this sort of infinite race, okay? So here's 0. So I pick constants c and k. What I'm saying is, for all n bigger than k, so wherever k is, I'm saying for all n bigger than that k. So this goes off to infinity. I'm saying if n is sufficiently large, then what? Math. We land on n is less than or equal to c. So for all n going off to infinity, n has to be less than c. Wherever this is, that means n has to be less than or equal to c. Okay, for sure there are values of n in here that everything's really great. But as soon as I get to, say, c plus 1, c plus 1 here is not less than or equal to c, but it is bigger than n. And what I'm saying is every number that's, it is bigger than k. What I'm saying is that every number bigger than k has to be less than c. That's clearly false. C plus 1 is not less than n. C plus 1 is not less than c, and it is bigger than k. And some of you might say, well, okay, well, that just happens if you pick c over here, but why don't you pick c, like what if we pick c, I'm going to call it c prime, over this way? Well, aren't these all going to be fine? No, they're not going to be fine because these don't even hit our initial criterion, right? We don't care about any of these because they're not bigger than or equal to k. So we only care about the numbers that are bigger than or equal to k, but they go all the way off to infinity, right? So if I'm saying pick any number that's bigger than k, going off to infinity, that number is smaller than a constant, that's false. That's a contradiction. And because there's a contradiction, I've shown that this is not true.